everybody. So today's kind of a big day. It's the last day that we're going to spend in this class studying the theory of groups. In the last couple weeks of the semester, we're going to change gears and study a different topic. So we'll conclude our study of groups with a big kind of culminating theorem. What the theorem tells us is that if I look specifically at groups that are finite and abelian, I can, in some sense, say everything there is to say about them. In particular, if I ask the question, what are all the abelian groups with a given number of elements? Like, what are all the abelian groups with 4 elements? Or all the abelian groups with 6 elements? There's actually a really beautiful answer to that. You practiced it a little bit on your worksheet for last class, but now I'll state the theorem that answers the question in general. So here's what the theorem says, and this is the fundamental theorem of finite abelian groups. It says, let G be any finite abelian group, then G is isomorphic to a unique group of the form Z sub n1 plus Z sub n2 plus Z sub n3, and so on up to some moment, I'll call it Z sub nk, where each of these numbers, n1, n2, n3, and so on, those are each equal to a power of a prime number. So what I want to now convince you of is that this theorem really does answer the question on the previous slide. In particular, it lets us list all of the abelian groups with a given number of elements, and it does even better, it kind of lets us list them without any double counting. Let me use some examples to illustrate what I mean by that. For instance, what if I ask the question, what are all the abelian groups with 6 elements? Well, the theorem tells me that any group like this must be isomorphic to Z sub n1 plus Z sub n2 and so on, where these n1, n2, etc., they should each be powers of prime numbers. And if I want there to be 6 elements in all, that means that when I multiply n1 times n2 and so on, I should get 6. And if you play around with this a little bit, what you can notice is that there's actually only one way to do this. The only way is to look at the group Z2 plus Z3. Notice here 2 and 3, those are both powers of prime numbers. Actually, they're both just equal to prime numbers. And when I multiply them together, I do get 6. So what we're finding here is that there's really only one abelian group with 6 elements. It's Z2 plus Z3. Or maybe to put it a little bit more precisely, any abelian group with 6 elements must be isomorphic to Z2 plus Z3. Now at this point you might say, wait a minute, I know an abelian group with 6 elements. What about Z6? I don't see that anywhere. But the reason I don't include that is because that's actually isomorphic to the thing I've already written down. How do I know that? Well, the theorem from last time tells me that because the GCD of 2 and 3 is equal to 1, Z2 plus Z3 is isomorphic to Z6. So I'm not going to write that one down since it's already isomorphic to something I have written. Let's try this same procedure in one more example. What if I want to know what are all the abelian groups with 12 elements? So, same idea. I'm going to express each one of them as Z sub something plus Z sub something else plus Z sub something else and so on. And all of those somethings, they should be powers of prime numbers. And when I multiply them together, I should get 12. This takes some thought to see how it's possible. But one way you might notice is to look at Z3 plus Z4. So 3 is a prime number and 4 is a power of a prime number because it's 2 squared. And 3 times 4 is equal to 12. So that's one example. But Z3 plus Z2 plus Z2, that's another example because 3 times 2 times 2, that's equal to 12. And 3, 2, and 2 are all powers of prime numbers. In fact, they're all equal to prime numbers. I claim in this case that those are the only two possibilities. So any abelian group with 12 elements is isomorphic to one of these two. And so as a sanity check, again, I think it's useful to sort of dream up the abelian groups with 12 elements that you can. For instance, what about Z12? Well, that one doesn't appear on my list because it's isomorphic to Z3 plus Z4. That again is by this theorem from last time because 3 and 4 have GCD equal to 1. If you're being a little bit more creative, you might say, why isn't Z6 plus Z2 on my list? And the answer to that is, again, it's isomorphic to something I've already written. In that case, it's isomorphic to Z3 plus Z2 plus Z2. How do I know that? Well, because if I look here just at these first two factors, Z3 and Z2, 3 and 2 are relatively prime, and so those two together are isomorphic to Z6, and the Z2 at the end kind of comes along for the ride. So we see that Z6 plus Z2 is isomorphic to something on my list, and that's why I don't need to add it to the list. So extrapolating from these two examples, I can now tell you a general procedure for finding all of the abelian groups of a given size. Here it is. So I'll tell you the procedure to find all abelian groups with n elements, and as I go, I'm going to illustrate each step in the procedure in the specific case where n equals 36, just to give you a sense of how each of these steps goes. Step 1 is find the prime factorization of n. So if I were looking for abelian groups with 36 elements, I'd find the prime factorization of 36, which is 2 times 2 times 3 times 3. Then step 2 is that I'll list all the possible ways to combine some of those prime factors into prime powers. Here's what I mean. First of all, I could just do nothing. I could rewrite the prime factorization, so 2 times 2 times 3 times 3. Or I could take those two 2's and combine them together into a 4. So I'll have 4 times 3 times 3. Alternatively, I could leave the 2's alone, but combine the two 3's into a 9. So I'll have 2 times 2 times 9. Or I could do both. I could combine the two 2's into a 4 and the two 3's into a 9. So I'll have 4 times 9 in that case. These are all the possible ways to take some of the prime factors in the prime factorization of 36 and combine them together into prime powers. So there's one more step to the procedure, which I'll show you on the next slide. Rather than trying to state this step too precisely, I'll just say each of these gives a group, but let me illustrate it in the example that we've been looking at. So in step 2, you found these 4 different ways of factorizing 36. So the first one was 2 times 2 times 3 times 3, and to that I'm going to associate the following group: Z2 plus Z2 plus Z3 plus Z3. And then similarly, if I combine the two 2's into a 4, then to that factorization, I'm going to associate the group Z4 plus Z3 plus Z3. Similarly, the factorization 2 times 2 times 9, I'll associate to that the group Z2 plus Z2 plus Z9. And lastly, the factorization 4 times 9, I'll associate to that the group Z4 plus Z9. What the fundamental theorem of finite abelian groups tells us is that this is everything. These are all the abelian groups with n elements. So, for instance, in the case where n is 36, what we're saying is that any abelian group with 36 elements is isomorphic to one of these 4 possibilities. So we're actually not going to prove the fundamental theorem of finite abelian groups in this class. It's a little bit beyond the scope of what we can do, but in our worksheet for today, we'll at least practice using it and see what we can get out of it. So I'll see you then.